Let's talk about quantum mechanics. It has this reputation for being just impossibly confusing. But what if the confusion isn't really with the physics itself, but with how it's always been taught? Today, we're going to explore a radically simpler and, frankly, a much more intuitive way to look at the quantum world. It's an approach that was pioneered by Richard Feynman, and it all kicks off with one beautiful, almost playful idea. Let's dive in and see how he rescued quantum mechanics.
So get this, back in 1949, when Richard Feynman first explained his new vision to the brilliant physicist Freeman Dyson, Dyson's first reaction was, "You're crazy." That's the kind of thing people say right before you change, well, everything. But Feynman, he wasn't crazy. He was about to give us an entirely new way to understand reality itself.
So what was this crazy idea all about? Well, to really get it, you have to look at the old way of doing things. For decades, the main tool for quantum mechanics was something called the Schrödinger equation. Now, it's incredibly powerful for sure, but it's also notoriously difficult. It's abstract, and it forces you to twist your brain into a completely new and often a really unintuitive way of thinking.
Exactly. As the biographers John and Mary Gribben put it, students spend ages just wrestling with all this complex math, only to find out later, if they're lucky, that there was a much simpler path all along. It's kind of like learning to navigate a huge city by memorizing every single street name, and then somebody just hands you a map. We're about to take a look at that map.
And this brings us right to Feynman's revolutionary starting point. He basically tossed out the complicated equations and started with one simple, almost childlike principle. And this one idea explains everything, from how a single electron behaves to the perfect arc of a baseball in flight. This is it, right here, in Feynman's own words. The electron does anything it likes. It doesn't just take one path. It doesn't take the best or most efficient path. It goes anywhere and everywhere, at any speed, even forward and backward in time. This is the absolute core of his radical idea.
So this idea has a name. It's called the sum over histories, or the path integral approach. And the core concept is just so beautifully simple. If you want to figure out the chances of a particle getting from point A to point B, you don't solve some big, hairy equation. Nope. You just consider every single possible way it could get there. The straight path, the loopy-loop path, even a path that goes all the way to Mars and back. They all count.
Okay, so how does this actually work? Let's break it down. First, you've got a particle that needs to go from A to B. Simple enough. Second, it explores all those infinite paths at the exact same time. Third, and this is the really key part, each one of those paths gets its own little rotating arrow, which physicists call an amplitude. Just think of it like a little spinning pointer. Finally, all you do is add up all those arrows. The final direction and the length of that combined arrow, that gives you the actual probability that the particle shows up at point B.
All right, so right about now, you're probably thinking exactly what Freeman Dyson was thinking. This is nuts, right? If every single particle is taking every single path, why does the world around us look so, well, normal? This is where Feynman's idea gets truly incredible, because it builds this perfect, seamless bridge between the bizarre quantum world and our everyday classical reality.
This is the big question, isn't it? When you throw a baseball, it follows this nice, clean, predictable arc. It doesn't seem to be exploring a path that takes a detour around the moon. So, what gives? How can both of these things possibly be true?
The answer is just so elegant. So while an electron explores a huge range of paths, for most of them, those little arrows we talked about are all pointing in random directions and they just cancel each other out. But, and here's the magic, there's a tight little bundle of paths, a pencil of paths, right around the classical trajectory. And in that bundle, all the arrows line up perfectly and add together. This is where you find the highest probability, and it taps into this deep law of physics called the principle of least action, which basically says nature is super efficient.
And this just lays it out perfectly. For a tiny little electron, that pencil of paths that actually matters is pretty wide, which is why its behavior is so fuzzy and quantum. Now, as the mass goes up, that pencil gets narrower and narrower. By the time you get to something as massive as a baseball, that pencil of paths has shrunk to be so infinitesimally thin that for all intents and purposes, it is a single line. The quantum fuzziness just vanishes, and you're left with the one classical path we actually see.
Now, this whole idea of exploring all paths isn't just some neat conceptual trick to explain why baseballs fly straight. This very principle is the engine that powers our most revolutionary, most futuristic technologies. It's the absolute foundation of quantum computing.
Think about it. In your phone or your laptop, a bit is simple. It's either a 0 or a 1. That's it. But a quantum bit, a qubit, is pure Feynman. Its state of superposition means it's exploring combinations of being both a 0 and a 1 at the same time. Just like a particle explores all paths between 2 points, a qubit explores all of its potential values at once. And that's exactly where quantum computers get their unbelievable power.
And the potential applications here are just mind-blowing. Because qubits can explore all these possibilities at once, quantum computers could solve problems that are literally impossible for even our best supercomputers today. This same principle is behind things like quantum cryptography, which promises unhackable communication. It even opens the door to wild concepts like quantum teleportation. All of this incredible power comes from that one simple idea: explore all paths.
So you see, what Feynman gave us wasn't just a new way to do calculations. It was a profound shift in perspective. It was a way to see the fundamental rules of the universe as being simpler and more unified than we ever imagined.
And like we touched on, this isn't some niche, fringe idea. As the physicist Thomas A. More says, this idea, the principle of least action, which Feynman's sum over histories is a quantum version of, is at the very core of modern physics. It connects everything, from classical mechanics to quantum field theory.
So here's the main takeaway. Quantum mechanics doesn't have to be the set of bizarre, disconnected rules that make no sense. If you just find the right starting point, it all flows from a single intuitive command from the universe: explore all paths. This one idea explains why an electron acts like a fuzzy wave and why a baseball flies in a perfect arc. It unifies the weird and the familiar into one beautiful picture.
And that kind of leaves us with a final thought, doesn't it? Feynman's approach proves that sometimes the deepest truths in the universe are hidden behind the simplest principles. It really makes you wonder, what other incredibly complex problems, maybe in science, or maybe even in our own lives, are just sitting there, waiting for us to find the right, simple way to begin?